So in this question we're asked to design a beam that's going to lift an engine with a dry weight of that much. We're told that a winch system is attached to the beam, which is going to be used to pick stuff up. Cool. And then we're told that we're going to be using an I-beam, and then we're asked to make the following assumptions about our configuration. So we need to have a safety factor of 3. We're given an I-beam with these dimensions, given a knockdown factor, given a load factor of that much, and an engine load factor of that much. Okay, so let's walk through our assumptions one by one. Safety factor is pretty self-explanatory. The I-beam thingy has a height of that much, a width of that much, but then m is your linear density. And m is this value here. So the units for that are going to be kilograms per meter, and yeah, kilograms per meter. It's the linear density. There's 3 types of density as far as I know. So you have linear density, you have area density, which is kilograms per meter squared, and then you have volumetric density, which is the one we are used to, which is kilograms per meter cubed. Reason why you would probably go for linear density opposed to like normal density is because it's only dependent on the length of your section. So when picking out standard steel sections, the height and the base are basically on lock. The thing that you change in your design is the length of it, right? So everything's manufactured to a specific height and width, and then the length is what you choose, right? And it would be quite annoying to calculate the area. So if we were to just take the density of steel, right, which is the volumetric density, we can get the volume of the section by saying the volume is equal to the area of the face times the length, right? So let's say we had our I-beam, right, as the question tells us. So we have our I-beam. Cool, it has a length of 6 meters, and then we need to calculate this area here, and then multiply that by the density of steel to get the mass of the beam. Cool. You could take the time to calculate the area, knowing that an I-beam has these nice little fillets and rounds in them. I'm just going to draw it like that. So your area you wouldn't be able to calculate very easily. It will also be very tedious. So they calculate that for you, and then they just say, okay, multiply by the length you're going to use to get the mass. So it simplifies the math a whole lot. At least I think that's the reason for them doing that, but in any case it just simplifies the math for us quite a bit. So yeah, we have that. And then we have our material knockdown factor of 0.9. So this is going to be applied to any material properties of your steel section. So the yield strength of our steel is going to be 350, which is typical of South African steels. I can't remember the code name for the steel, but yeah, you're going to multiply this by 0.9. So you're basically saying, okay, the strength of our material is 10% less than what we expect it to be, right? Which is pretty good assumption because we don't know what happens during manufacturing. The strength can vary quite a bit, right? So it could be less than you expect, could be higher. but we're designing for the worst case, so it's better to expect that it's going to be less than what we expect it to be. Okay, so we're going to multiply that by 0.9 when we get to that step, I guess. And then we also incorporate the dead load mass, the dead load of the I-beam, right? So the weight of the I-beam. And then we asked to apply a load factor of 10%. So we want it to be 10% more. We want it to weigh 10% more than what we expected to. So we're going to say the mass of it, so the weight times 1.1, right? Don't multiply by 0.1, because then you're saying you have 10% of the weight. You're not adding 10%, you're taking only 10% of the weight. Okay, then you have the engine load factor. Reason why you would apply that is because we're given the dry weight of the engine, which is that much, and then as you add oil to it, we're saying that, okay, the oil is basically going to take up, is going to weigh as much as 5% of the weight of the engine. So we're adding the weight of the oil as a factor of 5%, right? And then we're told that the beam is 6 meters long. So first step, free body diagram. So you're going to have your reaction forces, and then the weight is going to be basically a uniformly distributed load. Okay, and then we're going to assume that the engine acts in the middle of the entire beam. So the reason why you have it acting in the middle, so this thing is free to move around left to right. So it could be in the middle, could be there, but it's most likely to break the beam if it's in the middle. So that's going to be your point of maximum bending stress. So if you think about you trying to break a pencil, you'll support it on the ends, right? You'll kind of place your fingers here, and then you'd push in this location to try and break it, right? And that's the most effective way of trying to break a pencil. So kind of think of it like that, and this loading case kind of makes sense. Cool. And then so this is going to be 3 and then the force of the engine is going to be 6246 times 9.81 times our load factor of 5%, so 1.05. And then our distributed load, we usually used to having units of newtons per meter, but we're given this M value. This M value here is given as kilograms per meter, so we need to convert that. So to go from kilograms to newtons, we just multiply by 9.81, which is gravitational constant. So we say 67 times 9.81, which will give us 657.27 newtons per meter, right? Cool stuff. And then we can draw another free body diagram showing the simplified loads. So we have the reaction AY, BY, then we're going to simplify our distributed load. We're going to say 657.27 times the length of the beam, which is 6 meters, times our loading factor, which is 10%. and then our weight of the engine is 6246 times 9.81 times 1.05. Cool. Then you find your reaction forces using sum of moments and sum of forces in the y. Or you could simply say AY is equal to BY, which is equal to a half times the force, where the force is just these two combined, right? Either way you do it, you should end up with the same answer. And then the next thing we need to do is draw our shear force and bending moment diagram. And reason why you would do that is to find the location and the magnitude of the maximum shear force and the maximum bending moment, right? And then that will help you compute the maximum shear stress and the maximum bending stress. Okay, so I'm just going to draw the uniform distributed load in again for the weight, just so that I remember that I'm dealing with the uniformly distributed load. So if you don't do that, you might forget that this was originally a uniformly distributed load, and then you'll get your shear force diagram wrong. So yeah, just be wary of that. So the shear force diagram, starts at AY. So we jump from 0 up to whatever AY is. Then we have this distributed load acting downwards in that region. So we linearly decrease up until that point. This force is going to cause it to jump down. So we jump down to like that point there. And then again, distributed load. So we decrease linearly up until that point. And then this is going to cause it to jump up to 0. So we jump up like that. Okay. Then for our bending moment diagram, we start at 0. So the moments at A and B are going to be 0. Okay. Just because of the types of reactions that they are. So moments at this point are 0, and then we're going to jump up to some points over here, and we're going to jump back down to 0. And these points are connected by some sort of curve, right? And then this point over here is our maximum moment, and this is equal to the area of the shape over here. Okay. And then another thing, in order to determine how the graph is going to look, remember that bending moment is an integral of this line over here. So that's a linear function. So we expect the bending moment to be curved, right? And then the magnitude of it is basically the area of this entire shape, right? Cool. So it's going to curve upwards. So remember, the area is also positive, so we expect the graph to increase. So it's going to increase up until it reaches that point, and then shifts to negative after this discontinuity. So it's negative, it's going to decrease. Okay. And then notice how there's kind of like a sharp-ish point here. So if our shear force diagram was like that, so without any discontinuities, and it perfectly passes through 0, then our bending moment diagram would be a smooth curve, kind of like that. But because there's a discontinuity, which is this line here, because of that discontinuity, it looks like two curves kind of smushed together, right? So it's not one clean curve, it's kind of like two ones that are kind of squashed together. I hope that kind of makes sense. But basically, you're gonna have a sharper peak than you would if there were no discontinuities. Okay, so from that, hopefully you can calculate the maximum bending moment, which is just going to be the area of the shape here. And then your maximum shear stress is this value here, which is just going to be AY. Okay, then we need to calculate the maximum bending stress, which is going to be MY over I. And then I is going to be the distance from the centroid to whatever point you want to look at, right? So at the centroid, there's no bending going on. So let's say the beam is being bent like this, right? At the centroid, this is your neutral axis. So your bending stress at that location is 0. At the top, you're going to have tension, and at the bottom, you're going to have compression, right? The point that you're interested in is typically the point with tension, right? So this point over here, because things typically fail in tension. So we're going to calculate the distance from the neutral axis or the centroid up to that point, and we're going to call that Y. And because it's an I-beam, let's call this H. Because it's an I-beam, the centroid is perfectly in the center of the shape, so Y is just going to be a half times H. Okay, and then your value for I should be in the table, so you won't have to calculate that. And then M is basically your maximum bending moment, which is going to be this value here. Cool. Then for your shear force, your maximum shear force is given by this equation. Okay, and your maximum shear force will always be at the centroid of your section, right? So it's always going to be at this location. Okay, and then Vmax is your max shear force. Sorry, I think I said the max shear force is at the centroid. It's the max shear stress that's at the centroid. Cool. So that's your maximum shear force. Then Q is basically the distance from okay, it's kind of tough to explain it, but let's break this down. Over here you have a section with a uniform width, and the same over here, you have a section with a uniform width. Okay, so Y is going to be basically the area of one section with a uniform width. Okay, so we'll call this A1, and then, sorry, not AY, A1, and then we need to get the distance from the center or the centroid of that to the centroid of our complete object, right? We call that Y1. So Q is basically Y1 times A1 plus, and then we need to look at the next section, right? So we're looking at this section here. So we're going to look at this area. That's going to be A2, and then we need the distance from the centroid to that. We're going to call that Y2. So it's going to be Y2 plus A2. Hope that kind of makes sense. So it's basically the distance from the centroid to the area that you're looking at times the area of that section, right? And it's basically the sum of all of that. Okay, that's how you get Q. And then I is your area moments of inertia, and then B, if I'm not mistaken, B is like the width of the whole thing. I would have to check that. I'm not too sure. I think this would be B. Can't remember exactly. But yeah, I think there's an example of this in Shigley or something. Okay, cool. So now we can calculate the max bending stress and the max shear force. And then this is where your safety factors come in. So you might think to include your safety factors when calculating your forces, which you can do, you'll get the same answers, but it's typically not a good idea to do so. Apparently, I don't know, it's what the lecturer said. So your safety factors would come in now. So this bending stress that you would have calculated is your actual, right? It's your actual bending stress. Then now we're saying, okay, what if it's 3 times as more, right? So then now we're gonna multiply it by 3, right? That's multiplying it by your safety factor, and we're considering the case where the bending stress has like spiked to 3 times as more. Then it should be, and we're designing for that case. Okay, and then you do the same thing for your shear stress. So tau max will be tau times 3. Okay, so then now you've got your bending stress and your shear stress, and you've accounted for the safety factor. Now for the second question, we're kind of asking, what if the worst has happened and like our stresses are at this value over here, right? So our stresses are 3 times as high, and all of our forces are multiplied by this factor, so like they're higher. And then let's also say that our material is 10% weaker than it should be. So when all these factors are taken into consideration, what will our actual safety factor be, right? It was asked in a very weird way, but basically that's what we're asking. So in the worst scenario, right, our safety factor for bending is going to be our yield strength, right, our SY, multiplied by our knockdown factor, so KF knockdown factor, then divided by our maximum bending stress, right? And then this maximum bending stress is also considering the safety factor. So to be more explicit, so sigma B times our 3, our safety factor, right? So I know you kind of have this thing with the safety factor applied to it, and you're asking like, why would the safety factor not be 3? Again, we're kind of considering the case where everything has gone wrong and our stress is actually 3 times, so that safety factor doesn't matter anymore, right? Because we're already on the limit of like what we've designed for. And then our yield strength, so our material is 10% weaker than it should be. So let's say we've reached the worst case scenario where our yield strength is 10% less than it should be and our stresses are 3 times as high. So what would then be our safety factor? Are we still safe to operate, or is this thing just going to fail, right? That's kind of what we're looking for, because it's very good and well to like put a safety factor of 3 and like put all these load factors, but you'll find that your material is actually not capable of handling all those loads, because all the calculations we did before are load calculations. So from this point all the way down, those were all load calculations, but we never really went back to our material and looked and saw whether or not our material is actually capable of handling those extreme load cases. So we basically want to go back and check whether or not it can still handle our worst case scenario, right? So we made the situation worse and worse and worse. Now we want to like actually see, can it actually handle that worst situation? I hope that makes sense. So this is going to be 350 times 0.9 times whatever you get for this value here. So that times 3. And then for your shear stress, your safety factor for shear stress is going to be a bit different. So your allowable stress is equal to half of your yield strength. So that's the Tresca theory or whatever, right? So the way materials yield due to a normal stress is different from the way materials yield due to an applied shear stress. So from this, you can already see that it's gonna yield quicker due to shear stress alone, right? And if you remember in MSY, materials yield due to shear stresses, right? That's the mechanism for yielding. So we're saying that, okay, our stress for yielding, our tau allowable, is equal to half of the yield strength, right? So we won't even be able to apply enough shear force to get to the actual yield strength. It will yield at half of that. So we're saying that the material will fail twice as quickly compared to if it were to be if it were to be just in bending, if that makes sense. Hope that explanation kind of makes sense, right? So to get our safety factor will be our yield strength multiplied by a knockdown factor divided by 2, right? Cool. Then it would be divided by our tau max. Okay, then that will give you the safety factor due to shear. And this tau max is the yield stress that we calculated times the safety factor over here. Okay. I hope that explanation kind of makes sense, and yeah, hope this problem makes sense now.